All right. This lesson is called Derivatives of Trigonometric Functions Continued. Apparently there's going to be more trig derivatives in here. But we have to talk about one more concept in physics, which we don't beat to death too much, but I want to give you an idea, because it did come up in class. A couple people asked about, well, what about derivative of acceleration? And simply put, you can survive this course by knowing that jerk is the derivative of acceleration. It's the next derivative. But what does it mean? And to understand what it means is sort of difficult. And actually, I'm going to get sidetracked here for about 4 or 5 minutes. And if all the stuff I say next is sort of weird, or you don't believe me, or you don't quite comprehend it, that's okay the first time. Some of this stuff in physics you have to hear once, and then let it process and bang around. And then you come back the next day with what you think is a great question, going, yeah, but what about this? And then you hear the next level of the explanation. I argue that velocity is virtually impossible to feel. And by what I mean by that is, if you were in an airplane going across the sky at 300 kilometers an hour, you wouldn't give a second thought to throwing a ball up in the air and catching it, even though everything's moving at 300 kilometers an hour. That's sort of weird, right? It's moving through the air at 300 kilometers an hour, and you just go, oh, throw it up in the air, even though everything's moving at 300 kilometers an hour. See, velocity actually sort of becomes irrelevant once you're used to it. Think about the Earth. The Earth is hurtling through space at unbelievable speeds, and we're just like, yeah, whatever, because we're hurtling through with it. The only time you can really sense velocity is when you encounter something that's going a different velocity than you. You're like, oh, no, I can feel velocity in my car. I'm rumbling along. I'm like, yeah, you're feeling the ground, which is going a different velocity than you. So if you're cruising along, velocity is impossible to feel. I said virtually impossible because if I say impossible the first time, people completely don't believe me and they shut down. Let's jump out to a really weird example. Just imagine I'm out in space in my spacesuit, far enough from planets and the sun that I really can't see them too well. They're just in the background. I'm aware of them, but I can't really use them as reference points anymore. Then I see someone else coming in their spacesuit coming towards me, and they move towards me, and we go by each other in space a meter or so away. It's like we wave on the way by. They go by like this. And I go, wow, they were really moving. That was moving pretty fast. But they'd probably say, oh, Rob was really moving. You see? There's no way for us to tell who's moving and who's sitting still. In fact, it gets worse than that. There's no way to really say who's moving and who's sitting still. All we can say is what velocity we were in reference to each other. We're a little more grounded on the Earth than that. We've got the Earth as this big reference point to use, and we use that to try and figure out, and we go, oh, I'm moving this fast in reference to the ground. But it's not quite so simple as all that. Anyways, without getting sidetracked too much on that, velocity is tough to feel. Let's just say that for now, even though I argue it's impossible to feel. But velocity is tough to feel. Acceleration is not difficult to feel at all. You feel acceleration all the time. As soon as you're in a car and somebody hits the gas, you feel it, And we'll use extreme examples for now. Not when they gently touch the gas. When they hit that gas to pull out of the driveway, you're like, whoa, hang on. You really feel it when you get on the 403, right? Somebody goes to get on the 403 and goes on that ramp, and you're like, ah, and you're falling out sideways like this. You can feel that acceleration, that change in velocity that's happening there. But I argue acceleration's not that bad. Once you adjust to acceleration, you're okay, right? When you get into the car and somebody hits the gas for a second, you're like, okay, well, but then you sort of lean back into it, and everything's fine. Imagine a roller coaster you get on, and then even if it accelerates really hard, once your head's back on the thing, it's like, oh, but it's not that bad. You can feel it, but it's not that bad unless it's really, really accelerating, right? Jerk you can feel instantly. Jerk is how people get hurt. It's when the acceleration changes. Imagine you're jolting forward like this, and then someone slams the brake on. That's when you smash your head off the dashboard. Yes? Jerk is how much is the acceleration changing? It is hard to adjust to. When the acceleration changes, everybody has difficulty adjusting to that. Where acceleration can be adjusted to. I would say that's a level 1 explanation of jerk. Jerk is actually fairly complicated to understand, but that's like a level 1 explanation. Level 2 would be to talk about curving. Basically what we're talking about is acceleration is how much things are curving on the graph. If that curving is changing, we're talking about jerk. That's sort of a level 2 explanation. And we don't need any of those explanations for this course. All we need is jerk is the derivative of acceleration. That's all we really need so far. But you can see it gets pretty deep, and this is why it's a whole separate course called physics. It's because things get out of hand in a hurry, and there's a lot to understand. So let me read what it says here. A sudden change in acceleration is called a jerk. Yes? So now you are free to use that word with your friends and family, knowing, hey, whoa, Mom, I was just saying you did a sudden change in acceleration. That's why I called you a jerk. Notice they used Mom there, not Dad. Okay, when a ride in a car or a bus is jerky, it means the accelerations involved are not necessarily large, but the changes in accelerations are abrupt. Somebody smashes the gas down, you feel it. Actually, you really feel this when you're first learning to drive. It is hard to get that car to stop smoothly. Yeah, have you ever been in with a new driver trying to figure out the touch and that brake? And the end of that motion, it usually ends with everybody going, ugh, But someone who's good at it knows how to keep the jerk to a minimum. And that's the right terminology. You get to say stuff like that with a word like jerk. Jerk is what spills your soft drink. Okay, you're holding your soft drink like this. If someone's accelerating, you sort of angle it back a little bit so it doesn't get out of your hand. But then if they switch and turn to the brake, then you don't know what's coming, and your soft drink spills. The derivative responsible for jerk is the third derivative of position. So you start with position. You do derivative once, you get velocity. You do derivative again, you get acceleration. And then you do derivative again, and you get jerk. And they keep going like that. There's more like that. They're really hard to talk about. You really got to get into some advanced physics before you even care what's going on with that. Jerk's about the last one that we care about in most examples. Okay. So here's the actual technical definition. Jerk is the derivative of acceleration. If a body's position at time t is s at t, then the body's jerk at time t is dA by dt. Take the derivative of acceleration with respect to t, or it's the third derivative. See, I'm really pushing this Leibniz now. I'm only days away from being able to want to use these Leibniz notation. So I'm switching over slowly but surely. Hopefully you've seen them enough times now that you're not completely intimidated. Basically what we're saying is take the derivative of acceleration and look for t as your variable. You're like, yeah, well, of course. There's only one variable all the time. I'm like, I know. Next week, 2 variables. Not a big problem. Really, not a big problem. Recent tests have shown that motion sickness comes from accelerations whose changes in magnitude or direction take us by surprise. It's really the jerk that gives you motion sickness. Keeping an eye on the road helps to see the changes coming. A driver is less likely to become sick than a passenger who is reading in the back seat. So if you do have motion sickness a little bit, sit up front, look out the window, and let your body adjust to the fact that things are going on there. You stop looking out like that, and then when the car starts doing this, that's when you get motion sickness. Or if you just get old. I have found that as much as I was a roller coaster machine when I was a kid, as I get older, trying to manage those things is much more difficult. As you get older, the fluids in your ears and so on aren't quite so fluid, and then it's tough for your system to adjust when these random jerks happen on the roller coaster rides. What's going on? Oh, I was on there. Okay, good. Example, back to the pendulum or spring type example that may have caused you a little bit of heartache yesterday. A weight hanging from a spring is stretched 5 units beyond its resting position and released at time t equals 0. So we've taken a weight on a spring and we've pulled it down from its rest position and then let it go, and it's going to bounce up and down, back and forth. In real life, this bouncing would slowly degrade until it was back to its rest position. All the springs in our course will just keep going forever, and we'll deal with the math of slowing down later. Its position at a later time t is given by s equals 5 cos t. Determine an equation for the jerk. Well, I'm going to do all the equations to help you if you're having any trouble with the ideas here. And I'm going to break a mathematical form rule in the interest of teaching, a mathematical form rule in the interest of teaching well. We're supposed to have one equal sign per line, but I'm going to do multiple equal signs per line. Yeah, I know I haven't put a fifth form rule up there, have I? I've been thinking about it, what my fifth form rule is. I have to make a decision. Oh, soon. Yeah, anyways. S equals 5 cos t. So if I want the velocity, that's equal to s prime, which is equal to negative 5 sine t. And I broke the rule so that you can really see. You can call this v or you can call it s prime. V is more descriptive. V is the velocity, whereas s prime's a derivative. Yes? It's just a form thing. It can mess you up if you have multiple equal signs in a line like this. It's like, which one's the equation? Where can I move things over? So it's a form thing. It's not just a communication thing. It's to keep you out of trouble and keep equations on each line, not multiple equations like this. You're right. It is a small deal, and we mostly let you away with it. We don't get too excited about it. You won't see big X's on the page when you do it, but we try to avoid it when we can. But here, it's good. It shows what's happening here. V is S prime is negative 5 sine t. Those things are all the same. Then if I want acceleration, that's equal to V prime. It's equal to S double prime. Those two things are all the same. The double derivative of the position is acceleration. The single derivative of velocity is acceleration. And so here I get back to negative 5 cos t. I need to tell you that this particular equation isn't perfectly realistic for a spring bouncing up and down. The idea that everything would have period 1 here is a bit ridiculous. But we're short. We don't have the chain rule yet, so we're just going to do nice simple examples that aren't quite realistic yet. And a lot of math is like that. Let's do unrealistic, simple situations and work our way up to more realistic situations. Okay, so that's actually not today's lesson at all. That's just a review of previous lessons. Now here's jerk. It's like, look at this jerk here. Okay, jerk is the derivative of acceleration, or it's the double derivative of the velocity, or it's the triple derivative of position. And you really don't need all that. You just have to say, okay, well, there's the acceleration. Now I've got to do the derivative to get jerk, and I get 5 sine t. Notice that one more, and I'd be back to the original again. The fourth one comes back. That's an important thing for derivatives. It's not as important for simple pendulums and simple springs as it might look, because usually there's a period involved here, and the derivative will change each time. So don't read too much into that just yet. So I'm going to put jerk, and sometimes we put j at t, jerk at a certain time t. Determine an equation for the object's jerk at time t. Okay, I did that. There's an equation for the jerk at time t. So if they want to give me a certain time, then I can find the jerk at that particular time. At what times is the magnitude of the jerk the greatest? Well, there's a few different ways to do that, but I think the easiest way to do that is just to graph jerk. Just graph this jerk here. I'm addicted to that joke. Yeah, all right. Do, 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 do. 5 sine t. Okay, not a particularly tough graph I'm doing here. What do I need? Pi over 2, pi, 3 pi over 2, 2 pi. And the scale of this graph might clue you into I'm not using a particularly good equation for a spring bobbing up and down, because what are the chances that it does its bobbing up and down in 2 pi? Oh, yeah, why is 2 pi involved here? It should be like 5 seconds or 12 seconds or something like that. So obviously there's more work to be done here, but the derivatives we can't handle just yet. So we keep the situation simple and act like this is realistic. Okay, 5 sine t. So I got to go up to 5 and negative 5 and 5 sine t. Starts at 0, then it goes up to 5, then back to 0, then down to negative 5, then over to 2. Back to 0 again at 2 pi. Here's my graph of, now I need to label this graph so I know what I'm talking about, so I can make the right conclusion here. This is jerk. Equals 5 sine t. And the fact that it's not quite realistic here doesn't affect the conversation at all. You know, it's still, we can still have a conversation about when is jerk the most. And it says at what times is the magnitude of the jerk the greatest? When are you seeing the most jerk here? And I can just get that from the graph. I don't need any special tricks here. Yellow highlighter, I'm going to highlight when the magnitude is the greatest, right there and right there. Jerk 5, jerk -5. Those two particular jerks in this question are the most magnitude I'm going to see, the largest amount. So I'm just going to write that answer and then I see the question here. Okay, so yes. Because of the negative nature of this, let's say you had a drink in the car. At what times would your drink be in the most danger? And it's here and here, because this has, you're jerking forward here, and now you're jerking backwards there. And those are the times that you have a great chance of spilling your drink. Jerk is a maximum at t equals pi/2 and 3 pi/2, and I should have included one more word there, is a maximum magnitude. That's why I get away with using minimum here as well. Not a maximum, this is actually a minimum, but it's a maximum magnitude. It's the farthest from 0. We used those words a couple times with a couple people yesterday. How far are we from 0? And this is a very far distance from 0, so it's jerking backwards very hard. Oh, yeah, well, at what times is the magnitude of the jerk the greatest? So really, these should have on them plus 2n pi, and this one plus 2n pi, because this will happen again and again. There's these moments as this spring's moving back and forth where it's getting jerked the most. And where are those jerks happening? Well, they're happening when you get out to the edges of the motion there. Okay, we're not going too much farther with this. With this simple harmonic motion. It's more of an introduction to simple harmonic motion because we don't even have the equations just right yet. So we don't go too terribly far with this. Basically, a little bit of work on springs at this point. But do you have any questions about that spring? Now, so the jerk was sort of a side thing. It really got into trig functions there and a little bit more derivatives of sine and cos. I hope you found that derivatives of sine and cos, except for that negative, are not particularly overwhelming. In some ways, they're easier than polynomial derivatives. We thought that was easy. We thought bring down the exponent, reduce it by 1. We thought that was pretty easy when we started doing it. But comparatively speaking, sine and cos are pretty friendly, What we have to do today is look at the other 4 trig ratios and find their derivatives. So the derivatives of other basic trig functions, the derivatives of y equals tan and the reciprocal trig functions are shown below. Verify each of these derivatives on a separate page. Apparently, we have the skills to do these. It seems unlikely. When you look at tan, you're like, well, how am I supposed to know what the derivative of tan is? Well, let me write it down. I'm going to do these 4. These are 4 wonderful proofs coming up here. So I'm going to start with y equals tan x. And I'm apparently going to find its derivative. So you argue, you go, well, I don't know anything about, what are we going to go back to h's here? Is that what the plan is? And go through that crazy, proof that you did with sine, that thing? And the answer is, well, yeah, you could. What do we know at this point? The only weapons we have is we know the derivative of sine and we know derivative of cos.
So we could do the derivative of sine of the derivative of cos.
Change tan to sine over cos, and it immediately becomes a quotient, and we have the weapons for that. We've got quotient rule all ready to go. So I can do this derivative. Y prime equals, okay, with trig involved and a new quotient rule involved, these can be a little bit difficult, even though there's not much going on here. So I have to go very slowly. Derivative of the top times the bottom. And when we say times the bottom, again, what we mean is don't do anything with the bottom. Just write the bottom. Minus. Quotient rule is minus. Derivative of the top times the bottom. It happens all the time when you're doing quotient rule. You write a couple things down and then you start over and you go, okay, derivative of the top times the bottom minus derivative of the bottom. Okay, so that's cos x. Derivative of cos x is negative sine x. So that's derivative of the bottom times the top all over the bottom squared. And at that point, you're sort of feeling hopeless, like why, like this is not like going to be a nice easy derivative to memorize. It's not going to be on my memorization list when you're at this point of the proof. And then the next line comes along just going to tidy this up. Cos x times cos x is cos squared x. Negative times negative, that's positive. And that's sine squared x. And wow, look what just popped out of there. Yeah, wow. You know, like while we were beating sine squared plus cos squared to death in advanced functions, it seemed like, well, what's the big deal, really? Does this really come up all the time? And the answer is, yeah, it just pops out. We didn't sort of torture you with it for no reason, and it just pops out later. Sine squared plus cos squared is 1, so I get y prime equals 1 over cos squared, which is a legitimate answer, but not as simple as it could be. Because cos is 1 over secant, or secant is 1 over cos. So this is secant squared x. That is smooth stuff. And right on the chart there, do you see that derivative of tan of secant squared is right there on your little chart there? That is impressive. Quotient rule, trig algebra, and the Pythagorean identity all pulled together to find the derivative of tan without h's, mind you. I didn't go limit as h approaches 0. I didn't have to do any of that stuff, even though that could work as well. Let's try another one. Let's do cotan, because cotan is shockingly similar. I'll do the whole explanation again. I'm not trying to teach you today. I'm trying to teach you forever now when you see situations like this, when things look hopeless. You see cotan, you're like, what? You want me to go back to h's? All I know is the derivative of sine and cos, which are pretty simple. What could you do with cotan to get yourself into the cos and sine world? Luke?
You put cos x over sine x.
Yeah. Cotan is cos x over sine x. So now that trig toolbox I gave you, it's maybe got buried down in your binder. You're like, oh, maybe it's time to pull that to the front of my binder and keep it close by at all times. Yeah. So quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Now I did that pretty fast that time, because after doing a couple of these, you might find that quotient rule goes a little bit faster here. But I'm willing to slow it down to make sure we're okay. Derivative of cos is negative sine times the bottom. And when we say times the bottom, we mean don't do anything with the bottom. Just write down what the bottom is. Subtract derivative of the bottom, which is cos x, times the top. And so it doesn't quite play out quite as nice as the other one. I get negative sine squared minus cos squared all over sine squared. And that's a mess. Can anyone get me out of the mess? Yeah, take the negative out of it. So this is y prime equals negative sine squared plus cos squared all over sine squared. And then I get negative 1 over sine squared. And 1 over sine squared is cosecant. So this time it's negative cosecant squared x. Don't read too much into that negative. The negative is just saying, where does the slope start? Let's go back to sine and cos and try and revisit that a little bit. The reason that the derivative of cos is negative sine is because cos immediately starts decreasing, so its derivative has got to start off to be negative. It's immediately start going downwards. So it just has to do with who's going up and who's going down at any particular moment. So don't read too much into the negative. It's just lining things up for you so that you get the right derivatives. Oh, Mr. Bracket there. Whoop, beep. There it is. Another nice proof. Yeah, once you see a couple of these, you're like, oh, that's not so bad. I'm going to do 2 more before I'm done. Any questions about the cotan proof, though? What do I got to do? Secant and cosecant. I think I did a separate page for these on mine. Oh, more time here? Need more time here? Okay, secant. Y equals secant of x. And I'll use the same silly argument. It looks hopeless. However, we can express secant in terms of functions we know how to take the derivative and call that 1 over cos. And I think 1 over cos was in your homework. You did this last night. You find the derivative. No, maybe it was 4 over cos, was it? Am I remembering that right? A couple people asked me about 4 over cos. Yeah, so 4 over cos already appeared. You already did this proof. You didn't even know you were doing it. I know that's a constant at the top, and I said yesterday that when there's a constant at the top, there's another way to do it, and there is another way to do this one. But I'll just do it as a quotient rule because it's the easiest way to see it when trig's been mixed in here. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Let me just check that because I did that pretty quick. Derivative of the top is 0 times the bottom, which is cos x, minus derivative of the bottom, which is negative sine x, and then times the top, which is just the 1. I'm going to tidy that up and get a right answer. Sine x over cos squared x. Now I'm just going to play around with this because at this moment, this has 1, 2, 3 trig ratios and a divide sign. And I'm going to see if I can play around with it and get less than that, a simpler version of this. And the way I'm going to do that is I'm going to break this thing into 2 fractions. The first one being 1 over cos. So I'm going to break one of the coses out of there, and the other cos is going to stay with sine. And what I get is y prime equals secant x tan x. It's my favorite derivative of the trigs. It's so weird looking. Y is secant, y prime is secant tan. Such a weird result. And fairly simple. This didn't have to be simple. It didn't have to come out to be simple. Like, look back at the previous page there. For a while, this wasn't simple. Like those first lines of the derivative, it's like, oh, what a mess. I used to like trig derivatives. Sine was cos was negative sine, and then these come along. But they do play out sort of simple, not bad, when it's all done. What's the last one? Cosecant, which is 1 over sine. Same deal again. Quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And so when I simplify that, I get negative cos over sine squared x. This time it's cos over sine squared instead of sine over cos squared. A negative's popped out. Don't overread the negative. That's just matching up so that things increase and decrease at the right times with the graphs. Again, how complicated is this? 1, 2, 3 trig ratios with a divide. I think I can do better with different ratios. So I'm going to switch this to, I'm going to pull one of the signs out front here. I'm going to put the negative out front for just a moment. And then I'm going to be cos x over sine x over here. The other sign stays at the cos. That allows me to switch over to other trig ratios. So this is negative cosecant x, and this is cotan x. Not quite as tidy as the secant one. The secant one's nice. Derivative secant, secant tan. Yeah? Derivative cosecant, negative cosecant cotan. Just a little more awkward. Yeah, I hope maybe you can see why I'm listing this one as my favorite. Well, that's not true. My favorite is derivative of sinus cos. I mean, that's the best one by far. But this one has some beauty to it. Secant, secant tan. Like it's a real sort of beautiful result that comes out of there. Any questions about those proofs? In the second half today, we're going to talk about which proofs. Yeah? That's all I'm going to talk about. I'm going to do one more proof. I'm going to prove product rule later on today. And then we're going to say which proofs. You could nominate one of these for your list if you like them a lot. Not one of the, let's look back here. No, they're all good. Yeah, if you want to nominate one of these ones, I like these ones. And if your trig algebra is good, maybe you like them too. But we're going to choose 2. We'll hedge our bets carefully and go, okay, only 2. He's going to put one of these two proofs on, and I'll go through them in the second half and we'll choose. And that's all I'm doing in the second half. And in fact, the first half isn't going to even be the first half. I'm going to be done pretty early here because I think I only have 2 questions left to do. Am I right? Yeah. This kind of question came up in the homework last night and might have confused you about how to do equation of tangent when there's random trig derivatives involved. So I wanted to show, again, how to handle this. It says determine the equation of the tangent to the graph of f at x equals tan x over x at x equals 2. Now, we've done a bunch of these questions in the past. Most of the words we've done a bunch of determine the equation of the tangent to the graph f at x equals some function at some x value. So the difficult part here is dealing with the trig derivatives. Only the derivatives will be difficult here. So first, f prime. Oh, incidentally, I'm going to switch all those over to your, is it going to go on the memorize list? Or is it going to go on the stays on the board list? Oh, that's a good question. What will we do? What will we do? We will find a good compromise. Memorize. Y equals tan. Y prime equals secant squared. And what's the other one that y equals secant. Y prime equals secant tan. But I'll give you these ones if they come up. Y equals cotan, y prime equals negative cosecant squared. And then what was the other one? Y equals cosecant, y prime equals negative cosecant cotan. I don't know, we'll talk about that more tomorrow. I like this middle ground right now where you have to memorize these two, but you don't have to memorize these two. If you're really staring at them, you're like, oh, if you give me that one, I can think back of what that one is. See? These two are sort of closely related if you look at them long enough. And these two are as well. Secant, secant tan. Cosecant, cosecant cotan. But a little negative pops out of there. I don't know, we'll discuss that more tomorrow. About what's fair for your first time through these derivatives. Anyways, derivative tan, secant squared. So that's derivative of the top times the bottom minus derivative of the bottom times the top. Now, I did that fairly quickly because I wanted it all on the board. So you can look at each piece and go, do I understand each piece of this quotient rule here? The only really weird moment is that first moment. Derivative of the top is secant squared. So it's derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. Now this thing can be tidied up very little, in fact. And I really don't care. So I want to pause here and just talk about a little wisdom about these type of questions. Because I'm subbing in x equals 2 anyways, I don't really care about oversimplifying this thing. As long as it's pretty good, I'm pretty happy because I'm just subbing into it anyways. The only thing I'll say is your calculator doesn't have a secant button. That's the only real concern here. So maybe for subbing in, maybe I want to do a little better. And I'm drawing a line because you don't have to do this. If you're really good with secant, you know what to type in your calculator. But in case you're not great at secant, let me just say what we're really looking for is x, and then we're going to do 1 over cos x, and we're going to square that. That's how you type it into your calculator, because your calculator doesn't have a secant button. It's only got a cos button. So what I'm subbing in is 2 times 1 over cos 2 squared minus tan 2 all over 2 squared. And I encourage you to type this in your calculator to make sure you can make this happen. If you've got a good calculator, I mean, you got your really good Casio calculator, so you shouldn't have much trouble here. But let's see. Oh, am I in radians? Oh, setup mode. Yes, I'm in radians. Okay, radians is good. So fraction button 2 bracket 1 divided by cos 2, square that bracket, minus tan 2, and the bottom is 2 squared. Do you get 3.43? Approximately. See, sometimes trig works out nice. You get like a 7, or a 2, or a root 3 over 2. But this one wasn't nice. It was a crazy 3.43. So we're sort of stuck with decimal places here. Did anyone have trouble typing it in? Did you get 3.43? We getting some thumbs up? 3.43. And I'm going to write a sentence that you might want to put in your solutions to remind yourself when you're first learning about derivatives what it is we've got there. Therefore, m tangent equals 3.43. So we're well on the way to getting the equation of this tangent. I've got the slope now, 3.43. I just need an x and a y value. There's x equals 2. Also, y equals f at 2, which is tan 2 over 2. Tan 2 divided, I don't know why I'm having trouble typing in tan 2 divided by 2. Okay, negative 1.09. Do you get negative 1.09 when you, yeah, good. So then some of you are doing y equals mx plus b, and that's fine. I'm not trying to convince you otherwise. But an easier, faster way to handle this is for the equation is to use y equals mx minus p plus q. And so I get y equals, what was it, 3.43 x minus 2 minus 1.09. And if you really want y equals mx plus b back, then you can multiply out the brackets there and get y equals mx plus b out of it. And I think on the video I did that. I went to y equals mx plus b. But either way, you can leave it just like that. That is a perfectly defensible one. Now, when you're comparing with the answers in the back of the book, they might have gone to, for whatever reason, sometimes they just go to standard form. And I don't know exactly what their reasoning is about why they jumped to that, because it just said, equation of the tangent. There's an equation of the tangent. So unless they're specific about that, the only thing you're doing it like them so you can compare your answer, not because you really care about standard form. Is there any questions about that? I know it's confusing to equation of tangent in the middle of tough derivatives, but in the end, the steps for equation of the tangent are still the same. Find the derivative, so you've got the slope, get an x and y, and do your equation. So that those steps aren't difficult, except that they're in the middle of doing derivatives. You get distracted about this tough derivative, and you forget what it is you're trying to accomplish there. Any questions there? I think there's some tough ones like this in the homework, like some real tough derivatives. I can't say on the test I chose really tough ones. So that doesn't mean skip over them in the homework. Do them knowing that, hey, if I can land this one, then the one on Mr. Todd's test will be pretty straightforward. I'll just zip right through that, yeah? Do you need more time here? I'm trying hard not to rush, but you got lots of time today. Because we're going to take our break. No, you're going to have work time. We'll take a break, and then when you get back, I'll do one proof, and we'll discuss proofs. That's the only thing we have to do in the second half.
There's still one more example.
Yeah, I know. I got one more to go. Yeah, one more? Yeah. Determine the second derivative of y equals 7 secant x. Okay, second derivative. First derivative will be easy. Y prime equals 7 secant. Oh, this is my favorite. I love secant. Because to me, I don't know, the derivative just speaks to me for some reason. Secant derivative is secant tan. It seems impossible. Just like lots of other derivatives. Derivative of sine was cos. Seems impossible. How could it be that easy? Polynomials too. Just bring the exponent down and reduce it by 1. Yeah, great stuff. Much better than advanced functions, right? Advanced functions just seemed like we were trudging through the mud all the time. Everything we went to do was difficult. Derivatives is like, oh, everything we do seems to be nice. Tough algebra, I'll admit. Tough algebra at times. Wait till you see e to the x. Derivative of e to the x is e to the x. I got to teach that lesson one day. Mind-blowing. Oh, okay. Oh, let's not get sidetracked. I'm the one that's sidetracking. Then I'm saying, okay, focus. Find the second derivative, though.
Oh, is this product law?
Yeah, product rule. There's the first, there's the second. Oh, I did it with squiggly brackets. So when in trouble with product rule, go back to the squiggly bracket and say, there's the first function, there's the second function. So, slowly here. Y double prime equals derivative of the first, derivative of 7 secant tan. Oh, sorry, derivative of 7 secant. 7 secant tan.
Could we leave this a constant since it's just a coefficient?
Yeah. You can carry coefficients around, no problem. You could leave it out of the whole thing, but I incorporated it with the first function saying, I'm not scared of a coefficient at all. A coefficient causes me no trouble whatsoever because it just multiplies by the derivative. You know, derivative of x is 1. Derivative of 7x, 7. We don't really get excited about coefficients because they just multiply. So that was derivative of the first, and this question is really difficult if you don't underline things and keep track. That's derivative of the first times the second. So that's really weird looking, and it's tough to keep track of all those because there's multiple tans there. Plus derivative of the second, derivative of tan secant squared times the first, and I'm going to put the first in brackets so you can see it and stay organized with it. Now I did that pretty fast. I'm not implying that this is an easy question. Not at all am I trying to imply that this is easy and easy to keep track of all that because it's just not.
Could we factor out the 7 secant?
Oh yeah. This tidies up nicely. Y double prime equals 7 secant tan squared, and then this one is 7 secant cubed x. So I can pull out, what did you say, Luke? You liked 7 secant?
Yeah, pull that out and pull.
And what I'm left with is tan squared plus secant squared. And that's a mysterious little piece there because you're staring at that going, sine squared and cos squared is 1. Is this something too? And sometimes it is something and sometimes it isn't. Now, your trig toolbox has these on there. I don't memorize them because I really like this. You're starting to see why I love trig. If you just use your brain, trig will be there for you. I'm going to go over here and just work with this sine squared x plus cos squared x equals 1. I'm just going to work with that for a second, okay? And there's a part of your trig toolbox that has more of these. It's got sine squared plus cos squared equals 1, and then it's got some other ones. And I want to talk about where they come from. I see tan squared involved here, and that gives me a hint of what to do with this equation. I'm going to take this whole equation and divide them all by cos squared. I'm going to divide this by cos squared. I'm going to divide this by cos squared. I'm going to divide this by cos squared. And what I get is sine squared over cos squared is tan squared. Cos squared over cos squared is 1. And 1 over cos squared is secant squared. I've created a whole new identity. Well, I didn't create it. It's on your trig toolbox. But it's not difficult to see where it comes from now. Now that we got more experience with manipulating trig stuff, just dividing it all by cos squared gives me a whole new identity. And so what I get here is tan squared equals secant squared x minus 1. And so I can get this one over here. I can tidy it up even more. Y double prime equals 7 secant x. And I'm going to replace tan squared with secant squared x minus 1. And there's another secant squared over there that I almost forgot there. And so I can get this derivative all in terms of secants. Now, is it better? I guess I don't know. Is it a whole lot better than the previous one? Oh, we'd need a computer scientist, I think, to decide whether this was better or not. This one, how many operations? 1, 2, 3, 4, add them together is 5, times this is 6, times this is 7. That's 7 operations every time you want to run that line of code. This one, 1, 2, 3, 4, 5, 6 operations. It wasn't a grand improvement. And the only reason I did it was to show off a little bit of this, because we're going to need a little bit more of that as we go along here. I don't want you to think that that's the main part of what's going on here. In fact, if you left this on this test, if you left this here, I wouldn't grudgingly mark it right. I wouldn't be like mad. I'd be like, yeah, it's good. I like it. And I'd be anybody who did this stuff, like, yeah, here we go now. We're starting to really see the simplifications. Actually, I'm showing you that so that these moves don't seem so crazy with just regular coses and sines and secants and tans. You know what I mean? I'm trying to keep pushing the limit here so the easy ones stay easy for us, sort of. Yeah, all right. But do you have any questions about what I did? Excuse me, do you have any questions about what I did there? And then, of course, maybe they'd say, now find the second derivative when x equals 4, and you'd sub in 4 or pi over 2 or whatever. I mean, those parts are supposed to be easy. The subbing is supposed to be pretty straightforward.